we'll be talking about how we solved latency latency-sensitive queries at Facebook with our collaboration with Alluxio. So let me start by talking about Presto at Facebook scale first. Presto is a query processing engine. It takes SQL into input and does ETL and analytics related jobs for the users. Presto is pretty big in Facebook. It has roughly around 40,000 servers. Pretty much every day in Facebook, it scans roughly around 1 exabytes of data. Most of these jobs are ETL in nature. Data scientists are writing their pipelines, scanning data using Presto or writing using Presto. And there is a lot of ad hoc analysis done, which is done as well using Presto. And this ad hoc analysis and dashboards are very latency sensitive queries. And those were the challenges which we were looking to solve with Alluxio. So this is a very brief architecture diagram of Presto. By no means it is complete. It does highlights the important parts which we want to focus on for this particular task. So let's look into this. So we get the SQL and we have a component called planner and optimizer, which takes the SQL, parses it, tries to create different plans for it, and optimizes it. So the planner and optimizer, in order to able to do its job, it needs various partitions and files information so that it can create distributed plan and give it to multiple workers. Presto roughly has two main components. One is called coordinator, another is called multiple workers. So the current architecture of Presto is that it has like one coordinator doing work, doing the planning related things, and the workers are responsible for actually doing the real work. So the planner and optimizer gets the table and partition related information from Hive Metastore. And for those partitions, it accesses the HDFS, which is something equivalent we use in Facebook, and gets like the file block information from HDFS for those partitions. And then the scheduler, basically after looking into these files, it distributes this work for the logical plan it needs to execute to these workers. The workers interact with this remote data source, which is HDFS in this particular case, to open the files and read blocks from this. Workers in the Presto are compute only nodes. They do not really store any data with them. So which means like the only truth, the only data source which is in the HDFS, which is in the remote location. While this design allow us to scale because we can add as many workers as we want in the cluster at any point, it becomes a problem as well, because every time relying on a remote source can be a problem from the latency perspective, and which is something we saw. Why like this particular architecture was allowing us to grow as fast as we want. Like if we saw like, oh, we need like more load to handle for particular queries, or at the peak time, we can add more workers into it, and similarly the other way around. But as I mentioned, like this particular state, always relying on the remote data can be a big impact, can have a big impact in the query latencies. Okay, so let's look into like how we solve this problem. So one of the common optimization technique when handling with remote data sources is to cache the working data set closer to the compute node. And the idea is fairly simple. Basically, like you're making lesser trips to the remote storage for the data can help out not only with IO, but latencies as well. Okay, so this is a little more complicated diagram with our re-architecture. Again, it doesn't really tell the whole picture. but it all highlights the components which are important for this particular topic. So if you notice the worker communication with HDFS, we have a local SST in between. This local SST is available with every worker node, and it is storing some part of the data along with it. So that is the idea. Like if you are accessing any data from the HDFS, if the data is not available in the cache, which is this local SSTs, we will cache it. So the first preference would be going to the cache. So this is a read-only cache. So once so the data so this is the flow looks like. So the data request comes for the worker. Worker looks into the SST. If data is available, it reads it back. If the data is not available into the SST, like the cache is supposed to read the data from the HDFS and return it back. There are few more concepts like soft affinity is defined here. And the idea is behind the soft affinities, basically let's assume like a coordinator has around 600 worker nodes, which it is working with. These different workers might have different data set cached into it. So we wanted to create some kind of affinity to make sure we leverage the same worker again and again for the same data set for which we are executing. So how does this affinity gets created? So we talked about before distributing the plan to the workers, we get the file information from the HDFS. So based on these files, multiple splits gets created. A file may be a pretty big file. The file gets broken down into different splits. And for every split, this plan, along with the logical plan, gets assigned to the worker. So these jobs for the split, we try to make sure we have some affinity. So these splits have some kind of affinity with the workers. And this is what we call affinity worker. So before this new architecture, we used to have a random node scheduler. Random is probably not the right word, but the idea here, what it is trying to convey is the coordinator, it basically distribute the workload randomly amongst worker. Obviously, the workload is taken into the consideration to make sure like no worker is overused and all the workers gets used for the workload. But this kind of scheduling would not have been helpful if we wanted to build some kind of a data caching, because if a same split for two different jobs gets assigned to two different workers, then the same data might get cached into two workers, and that would not be the best use of the space available, because this space is not unlimited, it's limited disk space available in the SSDs. So we want to leverage the same worker again and again for the same split. So we implemented to start with something very simple. What it was we just take the split and whatever the path in the HDFS is available for that particular split, we just take them. We just divide it by the number of nodes, take the remainder of it, and assign that particular node. So as you can see, the algorithm in this particular case, what we started with is fairly simple. Like the split, take the remainder, choose the node, give it to the same thing. We obviously take the workload of a node into the consideration. If the worker has got too many splits already processing, we choose the different, the secondary. So the first one we call the preferred worker. The second one we call the secondary preferred worker. But even if the secondary is also fairly busy processing under the node, we choose the random node or the least busy node, which is available. And in that particular case, we do not leverage the data caching. This algorithm is fairly naive, and we can see this can be easily broken with the addition of a node or a node being lost. So we have already implemented the consistent hashing to make sure the node loss do not affect the data caching hit rates. Okay, so when we started working on this problem, we came up with a bunch of options. Facebook internally has lots of great caching libraries, which we could have leveraged. We had few open source solutions, and we started thinking about like, should we build our own? Um, so the Facebook internal libraries are great. They have lots of great functionalities, but some of them did not work for us, mainly because they are in C++ and we didn't really want the caching as a service. We wanted the caching to be embedded to make sure like it doesn't really get hit with extra latencies. And the another important point about these Facebook internal caching libraries was like they were not really an open source. And Presto being like the open source, we had great affinity with building solutions which are available to the open source world. Anyways, so we started with building something of our own, which was a pretty naive solution. We wanted to get started quickly and roll quickly. So we built something pretty naive. What it was doing, like it was just copying the warm storage files to the local storage as soon as it was copying. It was also merging these files to make sure like the file count remains limited into the local disk. We tried out our use cases with these things. And as you can see, like our cache hit rate was all over the place. It was like up and down all over the place. What we realized with this is that like because we were merging these local files into a bigger chunk, every time like the eviction event happened, we realized like we were evicting a large chunk of data. And we were not really finding reusable bits and pieces from these big files. So this is the point we understood more about our use cases, and we learned about Alluxio and we started collaborating with them. So what we realized, like we wanted like a Java-based open source library. We wanted segment-based caching. What does segment-based caching? What I mean by that? We wanted data to be read, write, and evict in a smaller portion or smaller blocks, not in terms of the bigger file units, because as we saw earlier, the eviction can evict a lot more data than it should with the bigger file evictions. We wanted like pluggable eviction policies. We wanted like different configurations. We wanted various stats for the cache usage so that we can understand uh, how is the cache performing, what kind of issues we are dealing with various failures like the software and the hardwares. We wanted to make sure like the caching doesn't become a single point of failure, which means like even if there are some issues going on with the caching, the operations must continue by ignoring cache and reading from the remote source. We wanted most of these operations to be asynchronous so that do not become a problem from the resource perspective. We wanted like better file management. We also wanted like the file throughput limiter to make sure we avoid the flash endurance issues. Um, so one of the things which I wanted to mention, like, so when we started working with Alluxio was available as a service, which was not our preference as we wanted to work with an embedded library. So we collaborated with Alluxio. We mentioned what we are looking for. Alluxio folks were pretty open for it, and we worked together to carve out a library which can be leveraged in the Facebook world. So performance. So we tried out like one of our use cases, and we tried out like 2 days worth of full queries from the production cluster, and we shared it to the shadow cluster. We roughly tried out around 17,000 queries. We tried it out on the 600 node cluster. Each node was configured with 460 GB of cache. We started leveraging LRU eviction policies, and we did with 1 MB block size, which means we were always reading, writing, and evicting in 1 MB size. So these were our performance results. As we can see, like we saw remarkable improvement in all across the numbers. Our P95 improved by close to 50%, similarly with P75. These are the latencies times in terms of milliseconds. Um, so some of our query, which was taking like 30 seconds, they started taking 14 seconds and similarly. IO savings. This was like a huge win from the IO savings perspective, which means for the data size where we were reading 582 terabytes of data, we now were reading only 250 terabytes of data. So we roughly had around 57% scan savings for this particular use case. The cache rate, which is fairly reflective of the latencies improvement which we saw, was fairly consistent. And as you can see, like it remained fairly almost picture perfect. There were some dips, which reflects of the queries, which basically like are rare, which doesn't really happen regularly, and they scan the data which was not really cached. So which means like there's some query which happens very frequently, very not very frequently, but it disrupts the whole cache. So this also tells about like some of the further improvements we need to do is like build some kind of a histogram and where we understand what kind of cache, what kind of queries might be the disruptive from the cache rate perspective. To further talk on the Alluxio deep dive, I will hand over this to Ben to talk about.
Yeah, thanks, Rohit. I will talk about some part of the Alluxio, focusing on the Alluxio part for this collaboration. As you may or may not know, Alluxio is open source data orchestration system, which is a new layer sitting between the compute and the persistent storage in the data stack. Alluxio is commonly used to speed up the OLAP queries for SQL engines like Presto, Hive, Spark, as well as like AI or machine learning jobs for engines like TensorFlow or PyTorch. Next slide, please. Yeah, a little bit more about Alluxio history. It's an open source data orchestration system, and it's originally originated from UC Berkeley AmpLab as the research project named Tachyon, was open sourced in 2014. The top contributors created this company and to continue to support and grow and commercialize this open source technology, backed by the top investors like Andreessen Horowitz. Today, the open source project has more than 1,000 contributors on GitHub all over the world. Next slide. Alluxio has been widely adopted by hundreds of different companies across different sectors all over the world in production, including financial services to retail or technology to internet companies. You can see a lot of big names, big logos on this slide as shown in this figure. Yeah, next slide, please. So the way people use Alluxio often is to deploy it co-located with or close to the compute processes, but with a different storage, either on-premise or in a public cloud, mounted into the Alluxio namespace. In this way, user can basically treat Alluxio as a data abstraction layer. You think you are dealing with a logical file system, and applications are only access this logical path in this logical file system without being aware of the real backend physical storage. Like you don't need to worry about which client to use, which storage parameters to use, which credential. All this can be handled by the admin setup together. Like so, the developers and admins can just use this freely without really understanding the details. This can greatly help simplify the development and decouple the evolution on both application side and storage or the data topology. So it helps also ease the maintenance of data platform in addition to the performance. Next slide. So for the collaboration with Facebook, Alluxio originally, as mentioned, is a full feature distributed system. But for this collaboration, I will focus on the development with Facebook to integrate Presto with a local library version of Alluxio embedded into Presto Workers. So this Alluxio local cache provides a HDFS compatible interface to Presto Workers. And this HDFS interface is backed by either both the external storage and the local directory to store the cache data. On the cache hit, it will just fetch data from local cache storage. Or on the cache miss, this caching file system will just go through this, go to the external file system to fetch data and put this data back into the local cache storage. Next slide. So here are some technical details when implementing this local version, embedded version of Alluxio Cache, particularly informed by Presto workloads running at Facebook. For example, first, in order to work with the non-sequential read pattern, which is reportedly commonly seen for ad hoc queries in Facebook, we choose to use the fixed size segments, as we call pages, to store data in the Alluxio namespace. And we also store them off heap rather than in the JVM on heap storage to reduce Java GC pressure. Secondly, because Presto server is highly concurrent by design, we have to implement a highly concurrent and thread-safe locking scheme to provide Presto workloads high performance, but also thread safety. Next slide. In addition, next slide, please. Yeah. In addition, we also introduce pluggable cache policies, including LRU as a default and LFU as optional. This cache library supports different storage engines, include Store, simply using a local file system as the storage engine, but also a more advanced storage engine based on RocksDB. We also provide a async cache write feature to help Presto to handle the bursty cache inserts. So this can support async cache writes, which queue the cache inserts in the background and run this in the background. Also, because we're running at Facebook scale, the disks we found it's in almost deterministically to run into certain problem, either hardware defects or the file system issues. It's basically deterministic. You can not assume the file system call to the disk will succeed or return you a failure signature in the bounded time. No, there's no such guarantee. It just simply because the large scale we're running. So we have to deal with this carefully to provide a failure recovery scheme, either during this cache transaction or during like a startup time. Next slide. So there's a lot of ongoing work. So we have already deployed Alluxio with Presto at a large scale, and it's running pretty well in production for quite a few months right now in Facebook. People are very happy about the result, but there is a lot of ongoing development. For example, to support the different level cache quota across in Presto. So the cache, we can just tell the cache, spend no more than 1 terabyte for this particular table or for this particular schema. We're also, as mentioned by Rohit, we see the dip in performance for certain cases, and we found oftentimes it's due to it's caching a lot of small files, and we're doing a lot of performance optimization for the small files. And for the future work, we're also discussing the semantics aware caching for different files. Can we do something differently? Next slide. Yeah, to use Alluxio local cache with Presto is pretty easy. You can see the 3 lines of change in the configuration on Presto side. And also we have a documentation, we have a blog documenting this. For all the technical details, you can also go to this link to read our blog. Next slide. This is my last slide. If you are looking for, so the embedded version of Alluxio Cache is basically providing you the basic functionality, but there is a lot if you are looking for a full feature caching control, distributed caching system. And this is something called Alluxio file system you can look for, including fine-grained control on the working side. You can free and you can pin data in the cache, or you can metadata caching and syncing, automate this process if there is any change on your backend. So you can just invalidate the cache in Alluxio space. And you can trigger the data transformation service, so you can convert certain formats into some other formats more friendly to SQL engines like Presto. Or you can trigger some migration service to move data from one storage to another, while providing no difference to the applications. From the application, they're still only accessing these logical files, logical directories. And we also provide a lot of centralized file system command lines, so you can easily deal with the data in the cache. For more details, you can read this documentation I listed below. Okay, so that's the end of my talk. I'm happy to take questions.
Yes, hey, hi Win. So we have a couple of questions Sam here on the audience. How do we manage memory sharing between DRAM and persistent memory? He asks.
I guess this is a question for me on the more on the Alluxio side. So for Alluxio, it's interesting that we have the concept like we're storing data on the off-heap storage, but we actually put the like running Alluxio in like using JVM memory, right? That's the DRAM. But you can use Alluxio to manage off-heap storage, which can be either DRAM or persistent memory, or a combination of DRAM and persistent memory, or some like SSDs. For Rohit, you can chime in, but like I know Facebook, they're using large volume SSDs to for Alluxio to manage as the caching space. So that's basically separation. Like the code runs on JVM using DRAM, but you can for the out data, it's off heap. It's not in the JVM, but you can combine directories from different persistent memory and DRAM, or the combination. It's basically up to your choice.
Yeah. So yeah, that was the I guess the next question was like, do you deal with zone storage?
I think as long as so there is two answers to this. So first, I guess like we need to understand better like what's the difference in the zone storage this audience is particularly interested in. But as long as you can integrate with Alluxio under storage, we have a called a persistent under storage interface. As long as you can integrate or compatible with that, then you can just write a plugin or use the existing plugin to talk to our storage. That's no problem. And if you're talking about multiple different zones, and as long as they are not migrating data to each other, and you can just treat them as a different storage and mount them into Alluxio space as just backing different storage directories, Alluxio logical storage directories. Or if you want to have enable more advanced logic across like a different zone storage, that might be harder, but like I'm happy to take this offline to understand the request better.